So if we've got a world that looks like that, with the crust, the outermost layer of the Earth, divided into roughly 20 plates, plates that are moving, there's only a few possibilities for how they can move. I have to go through my computer animation again. They can move past each other, side to side, as it were, or they can run into each other, or they can pull away from each other. A fourth possibility is they can just sit there and not move at all. And that does seem to be the case up in Siberia, where the North American plate contacts the Eurasian plate. That seems to be pretty quiet. But let's look at the areas where they're doing something more interesting. When plates move apart, we get a structure called a mid-oceanic ridge. And this is where what's going on is that new oceanic crust, solid rock at the bottom of the ocean basins, is constantly being produced at the mid-oceanic ridges. What happens is that in the gap between two plates, the mantle is primarily solid, but when you take a little of the pressure off of it, it liquefies, and liquid rock pushes its way up into the gap between two plates, turns solid, and forms new crust. And as it does that, it pushes the old crust away, and then more liquid rock comes in on the gap and forms yet another new set of crust, always pushing the older crust away. Another name for this process is seafloor spreading. And okay, I don't have a really good diagram of this, but you can see the effects right here. This is a map of the Atlantic. We've got North America over here at the upper right, upper left, sorry. South America at the lower left. This is Africa at the right, and then Europe at the upper right. And that red snaky thing that you see runs right down the middle of the Atlantic Ocean. That is the mid-Atlantic ridge. What goes on there is that liquid rock is constantly pushing its way up through this crack in the crust, right between the plates, right in the crack between the plates. Liquid rock pushes its way upwards, solidifies, and then starts moving in both directions away from the mid-oceanic ridge. New rock is always forming at the center of that ridge and then getting shoved out to left and to right as even more new rock forms. So liquid rock magma is always coming up and pushing those plates apart and then forming new crust. The upshot of all of this is that the oceanic floor is relatively young rock. The rock that's right along the center of that thing in the darkest red color, that's rock that's forming now. There's rock in there that formed yesterday. As you go away from the ridge in either direction, you see the color shifts from red to orange to yellow to green to blue. That darkest blue right there, the rocks that make up the ocean floor, just off the North American plate or just off the African plate, are about 150 million years old. That corresponding to when the Atlantic Ocean began to open up. That seems like an awful lot, 150 million years old, but most of the rocks that make up the Ozarks and the Ouachita Mountains are roughly 2 times that old or more. Rocks on the continents, because they're not subjected to this sort of thing, many of them are much older than this. But new seafloor is constantly being birthed along these mid-oceanic ridges. One of the few places where you can see it happen on land is Iceland. The mid-oceanic ridge actually cuts across the south end of Iceland. There's a deep valley there called Thingvellir, just outside of Reykjavik. And yeah, you can actually go there and you can stand with 1 foot on North America and 1 foot on Europe. Kind of a neat thing to do, I suppose. So, oceanic crust is relatively young. It's created at mid-oceanic ridges. And if new crust is being created, either the Earth is blowing up like a balloon, which it isn't, or crust has to be destroyed. And old crust gets destroyed at areas we call subduction zones, where one plate sinks under another. If two plates hit each other, at mid-oceanic ridges, they're moving away from each other. They can also be coming towards each other. If two plates with continental crust hit each other, they both crumple and make a big mountain range, like the Himalayas or the Washitas, for that matter. The rocks that Conway is built on are, crumpled like my grandma's car fender after she ran into that guy. They're crumpled because they've been deformed by extremely powerful forces pushing one continent into another. That's why if you drive out Highway 60, drive out Hogan Road towards 64, you'll pass through that big road cut where all of the rock layers are standing at about a 50-degree angle. That's a remnant of what used to be flat layered rocks that were crumpled in a collision between continents that formed Pangea. Anyway, so when two continents hit each other, they crumple. If an area of continent and an area of oceanic crust run into each other, the oceanic crust sinks under the continental crust and is ultimately destroyed. And we call the zone where this is happening a subduction zone. Subduction is the sinking of one plate below another. I should mention that a technical term for mountain building in geology is orogeny, Orogeny. And I won't test you on that, but I remember when you could get T-shirts at geological conferences with things like subduction leads to orogeny, which actually sounds kind of spicy, but it just means that one plate sinking under another leads to mountain building. And at subduction zones, we get oceanic trenches. And on one side of the trench, you get a chain of volcanoes called a volcanic arc. And here's what this looks like in cross section. You have oceanic crust moving this way and getting pushed down and sinking underneath a piece of continental crust. As it does, first of all, sediments and things that are on top of the sinking plate can get scraped off and stuck onto the top plate. Most of the city of San Francisco is built on scraped off sediments from a plate that has all but completely vanished, called the Farallon plate. And yeah, the rock that makes up San Francisco is smushed up deep sea sediment that was scraped off a sinking plate and stuck to North America. And where that plate sinks, not only do you get a trench, but as it sinks, parts of it begin to melt, and melting rock starts rising and punches up through the crust and forms a line of volcanoes parallel to the trench. That's a volcanic arc. I've got island arc written here, but it doesn't always form a chain of islands. So a better term would be volcanic arc. Now, earthquake waves, seismic waves, travel faster in cold rock than hot. And what this means is that by very carefully measuring the transit times of a lot of earthquake waves using a network of receivers on the surface, a network of seismographs. We can actually do a computer reconstruction of relatively colder and hotter zones in the Earth's crust. And we actually have a picture here. This colder rock is a plate. It's the Pacific plate that's getting pushed down under, I think, the Philippine plate.